If you haven't done so yet, pause the video and try to answer this question on your own first before listening on. In part A, the question tells us that the casters are locked, and what that means is that this cabinet is not free to rotate about this wheel over here at A, nor can it rotate about the wheel over here at B, because the casters, again, are locked. What we want to do for part A is draw the forces that are acting on this object. Now, we have one force that's pushing to the right and is labeled P, but we also have the weight of the cabinet itself, which will act straight downward, and we can label that W. In addition, we have the floor pushing up on the cabinet, and so we can show a force pointing straight up. And we can label that force NA. The N would stand for a normal force. We also have a normal force over here at B. And again, that's the result of the ground pushing up on the cabinet. Now, since this pushing force is directed to the right and the casters are locked, there's going to be an oppositely directed force pointing to the left, which is basically resisting that pushing force. So we're going to label a force acting to the left over at A and also a force pointing to the left over here at B. And those forces are essentially frictional forces, and we recall that a frictional force is equal to a coefficient of friction multiplied by a normal force. So over here at A, we can write the coefficient of friction, which is 0.35, multiplied by the normal force at A, so NA. And then over here, we would have the coefficient of 0.35 multiplied by the normal force at B. Now, since this cabinet is not accelerating, it's basically in equilibrium, we know that the sum of the forces in the y direction must equal 0. And we have three forces in the y direction. We have the NA and NB, which are pointing straight up, so those will be positive. And then we have the weight, which is pointing straight down, so we would have minus W, and that would be set equal to 0. We can add W over to the right-hand side so that we can see that the sum of the two normal forces is going to equal W. And furthermore, we recall that weight is equal to mass times gravity. So we can take the mass of the cabinet, which was 60 kilograms, and multiply by 9.8. And when we do that, we get 588 newtons. Now, of course, the sum of the forces in the x direction must also equal 0. And we can see that there is the pushing force, which is pointing to the right and is therefore positive. And then we have the two forces pointing to the left and therefore will be negative. So we'll have the minus 0.35 NA and then minus 0.35 NB. Now, if we added those 0.35 times normal force over to the right-hand side, we would see that the pushing force equals the sum of those two forces. And what we can do is actually factor out a 0.35, since they have that in common, and we would then have NA plus NB. But lo and behold, from the other equation, we see that NA plus NB is equal to 588 newtons. So all we have to do is take 0.35 and multiply it by 588 newtons. And we end up with approximately 206 newtons for the pushing force. So this is the correct answer to part A of the question. Now on to part B, which tells us that the casters at point B are locked, and the casters at A are free to rotate. So we want to come back here and draw the forces acting on the cabinet. Once again, we have the downward weight force of the cabinet. We have the two normal forces, so we're going to have the NA pointing up and the NB also pointing up. Since the casters at B are locked, we're still going to have that frictional force pointing to the left, and so we can label that as being 0.35 times NB. But the casters at A are free to rotate, so there actually is no frictional force opposing the pushing force over here. So we're not going to put a frictional force, in this case, at point A. Now, once again, the sum of the forces in the x direction must equal 0. We have two such forces, the pushing force that's going to the right, so it's positive, and then the leftward frictional force, which is going to be negative. And if we add that 0.35 NB over to the other side, we can see that the pushing force is equal in magnitude to that frictional force. This is a result that we're going to want to hold on to for now. Now, since the cabinet is free to rotate around caster A, what we're going to do is develop an equation for the torque around caster A. And so we recall that torque is equal to a force multiplied by a distance and then multiplied by the sine of an angle. And we also want to recall that any force that causes rotation in this direction would be considered positive torque, and then any force that causes rotation in that direction would be considered negative torque. Now that we've reviewed torque, we'll begin to plug in some of the torques in this situation. We can begin with the pushing force, which is marked as P, so that force would be P, multiplied by the distance from that force to caster A, which is simply the height, which was given to us as 600 millimeters, times the sine of an angle. Now notice the angle between the pushing force and the cabinet is 90 degrees, and that the sine of 90 is 1, so we can actually exclude that. And then we want to decide if it's positive or negative torque. As the cabinet is pushed to the right, that's going to want to rotate the cabinet in this direction about caster A, and as we noted, that direction is the negative direction. We can now move on to the weight force, where we take the force multiplied by the distance to caster A. Now, to see that distance, you want to extend the weight force and then measure the distance to caster A. It's basically a perpendicular distance. And we can see that that distance is half of the 500 millimeters, so that's going to be 250. And the sine of the angle is going to be 1 again because that angle is 90 degrees, so we're going to exclude that. Also notice the weight as it presses down at the center of the cabinet is going to attempt to rotate the cabinet in this direction, and once again that direction is negative torque. We can move on to NB, and we're going to multiply that by the distance from NB to caster A, which is the full 500. Once again, the sine of the angle will be 1 because it forms a 90-degree angle with the cabinet, and then we can see that NB is trying to rotate the cabinet about caster A in this direction. That is a positive torque direction. And then we can set this total torque equal to 0 since the cabinet is in equilibrium. Remember that the weight was 588, so we can plug that in. And then you'll notice to solve for P, what we need to do is come back to this equation and solve it for NB. So we can divide both sides by 0.35 and come up with an expression for NB. We'll plug that expression in over here for NB. And now we can do a little bit of algebraic cleanup. We're going to have negative 600p minus 147,000 plus about 1429p, and that's still equal to 0. We can combine the p terms. We'll add the 147,000 over to the other side and then divide by 829, and we should get about 177 newtons for the value of the pushing force. This is the correct answer to part B. Finally, over to part C, which tells us that the casters at A are locked, and now we're free to rotate the cabinet around caster B. So this is similar to part A, it's just a little bit of a switcheroo. We're going to have the normal forces NA and NB. We're going to have the weight force acting straight down. And then we have the friction at A, since that caster is locked, and that's going to equal 0.35 times NA. And then there is no friction at point B. Now, as before, the sum of the forces in the x direction is going to equal 0. We can see that there are two forces, the positive P force and then the negative frictional force. And then if we add that frictional force over to the other side, we can see that the pushing force is equal in magnitude to that friction force. Then we'll do the torque again. And this time the cabinet is free to rotate about point B, so this is our rotational point right here. We'll start with the pushing force, which if we extend it would form a distance of h to that point. So we would have P multiplied by h, which again is 600. The sine term will drop out once again, and that pushing force is tending to rotate the cabinet in that direction, and that's going to be a negative torque. We have the weight, which we want to extend straight down. We can see that the distance from the weight force to point B is going to be half of that 500, so that's going to be 250 once again. And that weight force, as it presses down, is trying to cause the cabinet to rotate in that direction. That direction is indeed positive torque. We also remember that the weight was equal to 588 newtons, so we can go ahead and plug that in. And then we have the NA force, which is a distance of 500 from point B. And that is causing the cabinet to rotate in this direction, which is again negative torque. Notice, by the way, that we're not including this force in our torque equation, and the reason is that if we extended that force backwards, it would pass through point B. Any force that passes through the rotational point is going to produce 0 torque. So that's going to hold for both that frictional force as well as NB. And that's why we're only including 3 of the 5 forces in our torque equation. That was true for part B as well. Now we can solve the first equation for NA, and we could see that it would be equal to P over 0.35. We'll do a little bit of cleanup. We'll have negative 600P plus 147,000, and then we'll have this minus 1429P equals 0. We can perhaps add the P terms over to the right-hand side so that 147,000 is equal to 2029P. Divide both sides by 2029, and you're going to get about 72.5 newtons for the value of the pushing force. So this is the correct answer to part C. Again, I just want to go back and emphasize why we excluded a couple of the forces in the torque equation. We're excluding the force NB because that force is passing through the rotational point, and we're also excluding this frictional force because that force is also passing through the rotational point. Any force that passes through the rotational point can be excluded from the torque equation. So you might want to go back to part B and just verify that 2 of the forces were indeed passing through the rotational point, and that's why we excluded them from the torque formula.